All right, I guess we're live. So let's get started in this case. And then I would say it's my great pleasure to welcome you all to our demo day today of the second edition of our Quantum Entrepreneurship Laboratory. Thanks all for being here, for taking the time, whether you are with us here in the Zoom call or if you joined on the YouTube live stream. It's a pleasure to have you all with us today, and I hope we have a entertaining program for all of you. With that, let's quickly look on what's on the menu for the next 90 minutes. So we'll start with a quick introduction about the Quantum Entrepreneurship Lab. So what's the course about and how is it set up? This also will give me the chance to thank a couple of people who helped organizing and kicking this thing off. And then we have a wonderful jury with us today that helps us to evaluate the pitches. And afterwards, we will have the main part of this event today, which are the 3 student teams that will pitch their results of the past semester. They will always have 10 minutes to pitch do their pitches, and then we follow up with 10 minutes of Q&A afterwards, where our jury gets to ask questions about their businesses. And then lastly, we have a quick outro. This is also where the live stream on YouTube will stop then. And on Zoom, everybody who is with us on the Zoom has the chance to talk to the teams directly in the breakout sessions. All right, with that, let's jump in. What is the Quantum Entrepreneurship Lab and what is it about? So we started the journey in March this year and asked for applications for our Quantum Entrepreneurship Laboratory. And we received more than 100 applications. So we really got to pick the 20 most outstanding participants for our course. So we have a wonderful group of students together here. And we gave them the chance to team up actually in interdisciplinary teams. And as you see here, we always have quantum natives together with some business developers. So bringing in the quantum background and the business background, as well as a software engineer. And I think from my perspective, at least, this is one of the most valuable things that this course brings, because over the last weeks, I could really experience that all of the different backgrounds, the students could learn just a lot from each other into each of the different directions. We had those 20 people in the beginning. We lost a few, so we teamed them up into 3 teams, and they got to pick their challenge partners. And we were very happy to that we had Eon, Merck, and IQM with us for this course to actually make sure the teams work on real-world problems and relevant problems during this semester. Looking into kind of how the course went over the course of the semester, we started with a kickoff week, which was 1 week where we had a lecture every day. The lectures were followed by a networking option for all of our students, so they could get to know each other and team up, look who they want to work with, and especially also what industry partner they would like to work with. So after the kickoff bootcamp and this week, we put them together in the teams and assigned them to their challenge partners. And then the first thing they had to do was, after getting the broader challenge together with their challenge partner, they had to come up with a couple of actual problems they would like to solve via quantum computing. So that was the first phase of the program, which is the ideation phase. And in the end of that, they had to pick actually the problem they saw as the most valuable to solve. And they could start into the prototyping phase for that problem. So really build their proof of concept, start working on their actual product. And during the prototyping phase, they had a midterm pitch where they could collect some feedback. And we kind of reiterated a bit where they could, which directions they could go into. And now we're kind of in the final phase, the delivery phase. So today is the investor style pitch, where they can show what they've done over the past semester. And then in 4 weeks' time, we also have a written days more the investor style pitches and just enhanced with a little bit of in-depth technology, but the main tech deliverable is still coming. As you maybe see on the slide on the bottom, I just briefly want to introduce the 2 organizations that helped this semester to put this course together. And firstly, I want to start with Push Quantum. So Push Quantum is a non-profit organization, and they're fully focused on bringing interdisciplinary and real-world focused education programs to students so that they can be set up for their careers in the quantum industry. So they are also the ones that created the Quantum Entrepreneurship Lab already in the last semester. But their offering goes way beyond that. I mean, they had, I think over the past months, they had a leadership series in quantum, where they had a couple of amazing speakers. This is free for all students, as far as I know. You can just sign up and join these courses. And then there's also the option to become a member of Push Quantum. But I think from what I've learned and seen so far, please always check the Push Quantum Tech homepage you see here below. The guys are always coming up with new ideas. There's always new offerings, so it's always worth it to check what's the latest and greatest they have to offer. And probably given such a course is quite some effort to put together, we were very happy to jump to their help as well in this iteration of the Quantum Entrepreneurship Lab from the TUM Venture Lab side. So that's where I'm coming from. And briefly on the TUM Venture Labs, what this initiative is about. This is something that the TUM together with the Unternehmertum has set up in the last year. And the focus is really to create more and higher quality spin-offs that are really technology-driven startups out of our research landscape here in Munich. And what we did for that is what you see in the hexagons here on the slides, is that we build really domain-focused individual venture labs. So there's different ones for aerospace, robotics, or healthcare. There's also one for quantum. This is what I'm looking after. And what we do in these individual venture labs is really focusing on certain technology domains and supporting startups really to bring their ideas into a stage where they can really incorporate a business. And we start there from education. This is why we are here today as well. But then we go into venturing. We try to offer access and offer infrastructure and build an ecosystem so that the startups have the right support network around them straight from the beginning. And I guess similar as for the Push Quantum guys, feel free to check our webpage to see what's the latest we have to offer. You see that on the bottom of the page as well. All right, as I said, such a course is always quite some effort and takes a lot of people to get running. And this gives me the chance to thank a couple of the individuals that really helped a lot setting this course up. So I want to start with our academic coordinators, Stefan, Christian, and Frank. Thank you all very much for pushing this from the academic side and giving us the option to have this accredited at TUM as well, and making it a proper university course, right? Secondly, we have our challenge partners, absolutely crucial element for the course, for the teams to work on actually real world problems and relevant problems. So thank you. We have Corey, Thomas, and Ines here as representatives. I think there's always a bit of bigger teams involved. So also thanks to everyone else on the team that has worked with our students. So thanks very much for doing this. This is a really helpful element and crucial for the course. What we do have as well during the course is always weekly lectures. And we had a great lineup of speakers and lecturers during this semester. So this is also a very valuable element. The next group of people is also very, very helpful, and a special thanks from my side as well to the guys here. Our teaching assistants who made sure that every lecture was actually recorded, was running, and were there for every of the teaching sessions and gave valuable feedback to the team. So Shexwan, Martin, Max, Esteban, Matthias, thank you all very much for doing that. I know it was a bit on a crazy ride at the beginning, and super happy that you were with us on this journey. Lastly, then we have the organizing team. So this is from the Venture Lab side, Klaus and myself. And then also, again, a special thanks to Push Quantum. And I'm very happy that we also have you guys with us today as a part of the jury, Raoul and Tom. So first of all, thanks for getting this thing started in the first place, but also for this iteration of the course, for actually helping us with all the support you gave from the beginning until this day, right? All right, so this is mostly it from my side in the beginning, but there's one group that is absolutely crucial for the event today, and this is our wonderful jury that we could get for this event. We're very grateful that you're all here with us, and I don't want to introduce all of you. I would suggest we just do a quick round of introductions, and I would hand over to Stefan, and would suggest we just go through the pictures as we have them on the slide. So Stefan, if you want to quickly do an introduction, stage is yours.
Sure. Thanks, Christopher. Thanks for the introduction. And so my name is Stefan Philipp. I'm professor at the Technical University in Munich for technical physics. And I'm also director at the Walter Meissner Institute. Briefly, my work is covering experimental superconducting qubit circuits and qubits and quantum computation with that. So with that, I'm very happy to see such a course now, which matches now the university to technology transfer company aspect. And I'm looking forward to the talks. Thanks.
Thank you, Stefan. Frank.
Yeah, hi, my name is Frank Homan, and I'm heading the chair for theoretical quantum metaphysics here at TAM. And I'm also joined Stefan in thanking all the organizers and participants in this great course. So I'm very much looking forward to what's coming up. So just very briefly about what we are doing. So formally, we are interested in understanding novel phases of matter. And for this, we have to often solve rather complicated quantum many-body problems. And with the advent of quantum computers, we are now very excited about thinking about how to use quantum computers for understanding quantum matter. Thanks.
Perfect. Thank you. Jan, if we have him on the call yet, I'm not sure.
Can you see me or hear me?
I can hear you at least, yes.
Okay, great. Sorry for being late. I came into a huge storm at the north coast. Now I'm here in a safe place. But anyways, so you're doing intro round.
Exactly.
So let's say a few words about me, or?
Yeah, just 1 or 2 sentences.
Okay, so yes, hello everyone. For those of you who haven't met me during the sessions, my name is Jan. My background is in physics. I studied and did my PhD at the Walter Meissner Institute in Munich, related to superconducting circuits. And then I moved to Finland. I worked there as a postdoc for 2 years. And then together with 3 other founders, we started IQM. And we're building quantum computers based on the superconducting technology. So great to be here today.
Perfect. Thank you, Jan. Then next, Henrik.
Thanks, Christopher. So yeah, thanks for having me. My name is Henrik. I was one of the founding members of Cambridge Quantum Computing. We're a quantum software company, and we were founded in 2014. And God, I wish a course like this had existed back then. So I think this is a great development. And now, just very briefly, we're a software company. We mostly do a compiler. That's our main product, and we have chemistry applications in machine learning, and that's broadly what we do. Yeah.
Perfect. Thank you. Then next, Emily.
Hi everyone. Really glad to be here today. So I'm an investor at Speed Invest. We're an early stage venture capital firm based out of Vienna. As most people here probably, or lots of the audience, I have a background in physics and 2D materials. Recently discovered the world of deep tech and realized this was the perfect environment for me to try to bring scientific credibility to the VC side of the table. And I spend most of my time at Speed Invest looking at quantum technologies. We've made a couple investments in the space already, and yeah, kind of agree with everyone so far. I think this kind of initiative is super important for the ecosystem, and really glad to see what's coming next. So thank you.
Thanks. Great to have you. Perfect. Benjamin.
Thank you, Christopher. My name is Benjamin. I'm a partner with UVC Partners. UVC is an early stage venture fund. Beyond that, I'm also supporting TUM Venture Labs as a director, so I try to contribute to the ecosystem as much as I can. I'm a board member with a quantum associated company, HQS from Karlsruhe, and I'm happy to learn more about the ideas we're going to see today.
Perfect. Thank you. Corey.
Yeah, hi everyone. Thanks for having me here today. So my background is also in physics. So I did my PhD at TUM here in Munich. And for the last years, I've been working at Eon Digital Technology as quantum lead there. So essentially supervising the quantum projects, scoping the quantum projects, and trying to bring things into production in real life. So really excited about today.
Perfect. Thanks for being here. Thomas.
Yeah, hello, my name is Thomas Emer. I'm with Merck KGaA, and also I'm physicist. I'm with Merck since 20 years, and 3.5 years ago, we did found a quantum computing task force. So I'm one of the co-founders. And what we really look is, of course, who's doing what in the quantum ecosystem, but we are also really interested to detect where we find things that have actual value, which is not so easy at the moment. And I'm really excited that we have this Push Quantum initiative. So I'm really keen to see what's going to be presented from the students.
Cool, thank you. Ines, you're next.
Hello, everyone. So it's also a pleasure for me to be here. I'm looking forward to the nice talks today. I'm the head of the Quantum Innovation department in IQM, where we are currently seeking to reach quantum advantage in several verticals, including also chemistry, and thereby our challenge today. And I'm also a physicist by training. I've been a researcher lately in the last few years in Munich at the LMU University, where I'm currently also a guest in the theoretical nanophysics department. So very nice to be here today. Thanks.
Perfect. Great to have you. The next row.
I'm not gonna try to compete in the experience game because we are in this room amongst giants. I'm humbled to be here. Thank you very, very much for making sure that this edition happened. I'm Raul. I'm at the intersection of entrepreneurship, and I did my master's in high performance computing with a specialization in quantum computing. And I'm a very strong advocate of applied educational formats. And this is exactly what I wanted to make sure that the students of Munich and beyond could enjoy through initiatives such as the Quantum Entrepreneurship Laboratory. With this, at the moment I'm still studying, and I thought that the best way to use my way until I can start my own quantum startup, as some of the people in this call, would be to make sure that the ecosystem is ready to build upon it. So thanks again to everybody. And now the stage is for Tom.
Exactly.
Hi, everybody. My name is Tom Hubrechtsen. Thank you very much for having me. I'm the president of Push Quantum. As you already heard our mission statement, I thought I elaborated just briefly on a bit of our offerings. So we've helped establish the Quantum Entrepreneurship Laboratory course. And we've also hosted Leadership in Quantum series, where we invited leaders in the field to explain about their career. Next to that, we're also setting now up a course in quantum machine learning, which we planned to be running in the winter semester of the upcoming academic year. And we're also putting a lot of effort into trying to building a community through meetups, which is of course a bit difficult at the time, but we're working on some concepts that we can bring together people in the Munich region so that they can network more. Next to that, I'm a PhD student at the Isaac Group. I focus on quantum machine learning. And last but not least, I would really like to thank Christopher, Klaus, Raul, everybody involved in the daily organization, as well as all the professors who supported the course. I think the course really adds value in preparing students for a career in quantum, and I'm really excited to see what the team's created.
Perfect. Thank you very much, Tom. All right, so this is our great jury for today to help evaluating the pitches. And I would say with that, let's jump into these pitches. We have first up Qnemics, and guys, I will stop screen sharing and would hand it over to you.
Can you hear me? Okay, perfect. Hi everyone, thanks for having us today. I'm Benjamin and I'm happy to present you Qnemics. So we have a problem. As recently shown by the floodings in Germany, climate emergency is coming. And renewable energies are one of the only way to go forward. So as you can see on this graph, there is no monetary incentive for private households to use renewable electricity. And on the other hand, energy retailers buy energy at volatile prices, but sell it to private households at fixed prices, and sometimes even lose money when prices are above the fixed contract customers have signed. So I'm going to hand over to Mauricio to present you our solution.
Thank you, Ben. So we wanted to do something about it. And that's why we decided to start Qnamics. We want to provide dynamic green energy. Our software solution really targets both the electricity retailer and private households. We help energy retailers to sell electricity dynamically, and we help private households to consume as much renewable electricity as possible at the cheapest prices. How does it work? Well, smart meters installed in private households send the necessary data to compute real-time updating prices, which we provide to the end users. But we don't stop there, because we provide discounts whenever energy is green. As you can see here, prices are not fixed anymore, but they are dynamic. But we don't stop there, because whenever there's a surplus on renewable energy, we provide discounts on the price. This way, end users have the possibility to switch to time slots where energy is green and cheap. The energy retailer really gets a whole package where he can see for each individual customer what the current optimal price is. On the other hand, private households get an overview of the current and the forecasted energy prices during the next hours and days, which allows them to shift their consumption to points where it's beneficial for them. To sum it up, energy retailers can maximize profits while minimizing risks, and private households have the chance to engage in consuming renewable energy at the lowest market rates out there. And now I'm going to hand over to Romain, who's going to show you our solution.
Hello, let me give you a quick tour of the platform we built at Qnamics. For now, let's be John. John is using Qnamics pricing subscription and wants to know real-time and forecast prices for his energy. So John grabs his phone and logs in our mobile platform. He immediately sees the real-time price and the green share of his energy mix. To put this into perspective, he can compare with the average day price just below. Finally, he can spot trends in his consumption for the day, the week, the month, and even the year. But knowing the current price is great, but John wants to go a step further. Indeed, John wants to act for our planet and his wallet by consuming green energy at a cheap price. In the Trends tab, John can access a 1-day and 3-day forecast to schedule his dishwasher when energy price is the cheapest. So for instance, in the early afternoons there. Eventually, John likes to play and share, and the profile types give him an overview of his behavior and a public shareable URL to share with his friends. We can come back to that later if you're interested. Let's now become Paula. Paula works for an energy retailer and wants some feedback about the state of the solution. Through a laptop admin interface, she gets an instant overview about the revenue, profit, and energy provided. Qnamics pricing algorithm is based on the green share of the energy mix and is thus very local. Paula can use the map view to investigate any region green share, price, and consumption. She can even compare regions to get more insights. If she wants, she can dive into more precise data for every region. She can see the spot price, the price, and even the profit, as well as the energy mix. That's it for the Qnamics platform tour, and Xiaoming will now explain how Qnamics works under the hood.
So now let's talk a little bit about the backend, how our algorithm works and what kind of data do we need. So as mentioned, because of the smart meter, we can easily collect the consumption amount of each individual customer at each individual time slot. So basically, we collect 3 different kinds of data: the green energy intensity, consumption amount, and also the current spot market price. Based on the 3 different data, we can calculate the behavior score. And based on this behavior score, we are aiming to maximize our social behavior, and we want to assign the discount. So our problem here is basically in a classical solution. This is a combinatorial optimization problem with 2 constraints. One, we want to ensure that every customer has equal chance for discounts. So this is a fair play. And secondly, we want to use this behavior score we just defined to assign the discount. So basically, who performs better will get a better discount. So let's look at this problem with 2 naive constraints. A naive solution will require all different kinds of permutation, and the problem will scale with the factorial of the problem size. But within the with the quantum annealing layer, we can map this problem into a discrete quadratic model. So this is basically an extended Cooper problem, and we can map this problem to our QPU, and we can solve it quite easily. So now let's look at how are we going to reformulate our problem into a DQO problem. So basically, as mentioned, we have this behavior score based on 3 different kinds of data. Based on this score, we can calculate a priority table. And based on this priority table, we can see that 2 constraints we introduced before are automatically satisfied. And now we can easily transforming this problem into a scheduling problem, which is a perfect suitable problem for the quantum annealing layer. So in the next slide, we are going to talk a little bit about the data processing stage and also the challenge and outlook we are facing.
Thank you, Xiaoming, for that. And as he briefly mentioned, we have now transformed the problem into a scheduling problem. And this now is sent to the D-Waves Ocean SDK annealer, which solves it and returns back the result over the cloud and assigns discount values to individual customers based on their consumption scores and the consumption's behavior that we have obtained previously. This works quite well and scales up quite nicely, but there are some challenges and some things to look forward to. The challenges mostly being governed by our hardware, the limited qubit availability, the problem type, as well as the architecture of the computer involved. Annealer offers definitely many performance improvements over classical solutions, and as I mentioned, it scales quite well. But right now we are restricted a little bit by the number of available qubits. The D-Wave annealer has about 5,000 annealer qubits available for general solutions. However, the good thing is that by 2023 or sometime around that year, it's predicted to reach about 10,000 qubits, which will definitely be a big boost for businesses seeking to utilize such problems. And the best part is that there's also a possibility of mapping such optimization problems to gate-based universal systems running comparable algorithms such as the Quawa. And the advantage being that they have potentially more speed up and some more better theoretical guarantees. So that was about the challenges and outlook. And now I will hand over to Benjamin to talk a little bit more about the momentum.
So regarding the market, there is an incredible momentum for QNMX nowadays with a CAGR of around 15% per year. This CAGR is driven by 3 trends. The smart meter rollout everywhere in Europe, the momentum of renewable energy as explained during the introduction, and the new development of quantum computing that is going to enable our solution and help us to develop it everywhere. Our market size is around 7.5 billion in Europe. The sum is about 1.2 billion in Germany, and our current market reachable is 1.5 million in Germany because we only have 50,000 of smart meters nowadays, but as said before, the market is growing. Let me now hand over to Jenny for the competitive landscape.
On the current market, there are on the one hand side, the classical energy provider that also offer partially green energy tariffs. And then we have solutions like price comparison platforms that help customer to get an overview of the different prices. And there are companies offering dashboards for visualization, for example, of smart meter data, and a few startups offering dynamic energy tariffs. QNMX is going to combine and improve the different aspects, and we are the only dynamic energy pricing solution based on quantum that offers discount on green energy. And the customer of our solution will be the energy retailer that will pay a yearly subscription fee to cover the overhead. And we are going for a usage-based pricing to cover the variable cost. And to implement our solution, we have an interdisciplinary team with deep knowledge in quantum computing, software development, as well as entrepreneurial finance and strategy. And we as QNMX are looking forward to help the energy retailer to sell the energy dynamically and also to help the households to consume more green energy and to make a contribution to the environment. And if you're now curious about our solution, you can check out our dashboards by simply scanning in this QR code with your smartphones, and you can use the credentials below to log into the dashboard. And now we are looking forward for your feedback or questions or any comments you might have.
Great. Thank you very much, Dynamics, for this wonderful pitch. I would say with that, let's jump into the Q&A. And I'd suggest whoever has a question uses the hand symbol. I see already one from Stefan. So you can go first, Stefan.
So thanks for the nice presentation. So I would have a question on the quantum solution and the time scales involved, because it's not clear for me how fast you have to react to this dynamical energy market situation, and what would be the expected benefit and from the quantum solution to speed this up. Do you have a good understanding of what speed up you need actually from the quantum to handle the situation properly?
Okay, I think I will take over this question. Thank you for the interesting question. And for this time slot I just mentioned, this is quite flexible. So as we know that in the energy market, it is traded every 15 minutes. So basically, we want to expect maybe the maximum, so the most frequent time slot we are expecting is 15 minutes. But for the current stage, it can also be like every hour, every 2 hours, or a quarter of the day, or every day. So to expect the quantum speed up, like we have seen here at the adiabatic, because this solution based on the quantum annihilator. So basically, quantum annihilator only provided an empirical speed up. So for some researchers has discovered there's a speed up, basically a square root speed up. So basically, it's a polynomial speed up or some sort of thing like that. So we expect that our quantum solution will have an easier formulation of the problem, first of all, and also regarding this flexibility of choosing different time slot, they will speed up the problem compared with the classical solution in the next few decades.
Okay, thanks.
Wait, I think Henrik was next.
Did you say me?
Good. You got to unmute yourself. Yeah. I have a follow-up question on that, actually. So do you know, so you mentioned that the time frame by which you have to react is 50 minutes or 50 minutes to an hour. Do you know, based on the number of data points that you have, maybe taking into account all, I don't know, smart homes that exist in Munich or whatever, something like that, do you know what the state-of-the-art classical solution would be? Would that fit into the 15 minutes, or how long would that take? Or when do you hit the ceiling? What's the maximum amount of data points that this breaks?
Right, Xiaoming, maybe you can elaborate a bit more like on the current amount of users we can handle and about how we can do a shortcut with that by segmenting it. I think that would be...
Okay, I will take over this question as well. As you just mentioned, what is the data size the classical solution can handle? And actually, this is a very good question, and I expect it can handle quite large data sets. But the problem is the current dynamic pricing that was implemented in the market doesn't be that frequent. So basically, dynamic pricing is based on a decentralized energy market trading is basically a very new topic, a very new area. So we haven't seen much classical solution out there. And regarding the quantum solution, it's basically the 15 minutes is the upper limit we expect, but currently we expect our algorithm to work well and to compete well regarding the speed up and the accuracy compared with the classical solution for a few times a day, so basically a few hours a day, and up to 100 or thousands customers.
All right, I think Frank was next.
I think my question mostly has been answered already, but just maybe regarding again, because you said that there's a scaling like speed up, like the quantum algorithm compared to the classical algorithm, like a square root improvement, right? Did I get it correctly?
Yes, but that was based on basically a pure experimental empirical comparison. This is not, because as we know that we did not expect a quantum advantage for the adiabatic quantum computing. Right? So basically our solution, the advantage of our solution is we expect that when basically the quantum error correction is improved regarding the gate-based quantum computing. We can map our problem to the gate-based quantum computer, and starting that, we can get basically a theoretically proven speed up as expected.
I see. And in order to have some system that would be competitive with current classical solutions, how many qubits and what kind of error rates would you need? I mean, just to have an estimate.
Yes, we actually have taken that into account, but we didn't have like the exact number. For example, what exactly is the tolerance for the error. But we are doing this problem by subsidizing the problem size. So basically, we expect. So some people might think that we will run the problem of like the whole customer cluster, a few thousand, 10,000 million customer, but in the reality, because also you have seen at the data post-processing stage, we have to give the discount based on the individual consumption behavior. This is not only based on this priority table, which reflect only the real-time consumption behavior. We also have to take their long-term consumption behaviors into account. So in that aspect, we are expecting to cluster our customer beforehand. So basically, in the data pre-processing phase, we can basically cluster different customers, and based on that, we can reduce the problem set. So we might we have a few thousand qubits available, but in the reality, maybe we just need a few hundred qubits to run for like 1,000 or a few thousand customers, and if we run the problem different times for different customer clusters. So this is the problem for us to handling the current data core of the quantum computing.
Okay, thank you.
Thank you for your questions.
Good, then it's Raul and Tom after that.
Thank you, and thanks for the nice presentation. I'm gonna take the discussion to the business side, as I see this obtainable market that you pictured, in which you were assuming that you were gonna take over the whole market for smart households with smart meters in Germany. Are you assuming a market take of 100%? This is the first question.
Okay, I'm going to take it. So in this graph, we assumed we take 100% indeed.
Okay, and let's say that tomorrow some of our outstanding investors decides to put some seed round in this idea. How would the first year look like? Because I'm missing some kind of roadmap about how are you going to bring this vision into reality?
It's a really good question. So basically, it would depend on the amount given. I think at the beginning, we might need 2 or 3 years of R&D to really develop our solution, have something really strong, and be able to have a good size of computer to do it. And once we have a good product, we might need to develop it and to sell it. So money at the beginning would be focusing on R&D, I think.
Yeah, just to add on that, we thought about the roadmap. So actually, we are still in the phase where we have to develop the concept and prove it. Afterwards, we're planning to do MVP, but with a clear partnership with an energy provider that already showed some interest. We're obviously going to beta test it, but that's going to be in 2022. And then the rollout and the finalization is going to still take 3 years. So we will probably focus now in terms of investments on public grants and business competitions, but not on investors right now. And once we have something that is has a validated value and we have a finalized product, then can think about actually going for venture capital money or anything in that space. But before that, we're really focusing on development and research grants probably.
That's an excellent answer and brings some more clarity. Just in case you're actually thinking about bringing this forward, it may make sense to consider just putting a classical solution as of today in order to be able to deliver value to your customers as soon as possible, and therefore you won't be having to burn as much money until you break even. just as an idea, but of course you can also go for this approach in which you put all of your investment into quantum.
Thanks, Earl.
Great, Tom, if you want to go ahead.
Thank you. Yeah, so thanks for the presentation. I have about 2 questions. The first thing that I would be interested in is who exactly is the customer of the startup? Is this being sold to end users, or is this being sold to Ian, or who did you define as your customer?
Right, so I can take this question. Maybe Rama, first you want to show, yeah, the slide, perfect. Thank you so much, Rama. So as you see, we have 2 stakeholders you clearly mentioned, and both profit or benefit of it. However, the paying customer will be the energy retailer. The value for the private household is that he can have cheaper prices, so it wouldn't make sense to put further strain on their budget. And it, like, the incentive to switch to a dynamic pricing model should be high enough that we can convince as most of customers as possible. However, and now Roma, maybe you can switch to the 4th slide of the appendix. You may ask yourselves, like, is it possible to maximize the profit for the energy retailer while offering cheap prices for the end user? And actually it is, because we try to secure the current profit margin of the energy retailer, that is with a fixed pricing, but we try to add on that. So actually with our software, the energy retailer can decide to actually add on its current margin and to optimize the prices according to that. So with our solution, there's an increase in profit for the energy retailer, and that's why we charge a small, we charge for that. Now, considering the question who's paying for that, you may want to take a look at here. So basically, when renewable energy, there's a surplus, then the provided price falls during, let's say, 7 a.m. and 7 p.m. And end users pay a cheap price. However, when energy is gray, for some reasons, or because renewable energy, solar and wind is not working, then the prices are going to increase. So there's a price premium for that. So in that sense, end users who are consuming energy at those times pay for the discounts of end users who are consuming renewable energy. And that's basically to incentivize the usage of renewable energy, but also ensuring a higher margin for the energy retailer. I hope this somehow is an answer to your question and gives more insight into how the economics work.
Yes, thank you. So part 2 of the question would then be for Ian. So if I understand correctly, there's 2 reasons in order to invest in this. And the first one is that it gives the user the idea of the dynamic pricing. And the second one, they could have the extra savings on top of this. Did you go to the end users and did you check how many of the users would be actively using this option and to which extent, and how much money would this then address?
Right. So I'm trying to fit my answer in the remaining time, and I hope I will manage it. So first, Roma, can you please show the personas we developed, and maybe first in the backup slide, starting with the energy provider? That would be great, actually. So yeah, one, I think it's, yeah, so we can stay here. Well, it's a lot of text, but I will summarize it. So the energy retailer has not only the value proposition that it gets a high profit and decreased risk, but it also, when we talk to energy retailers, we figured that they have somewhat of a difficulty in rolling out smart meters in the German market, because German end users are a bit skeptical about smart meters. But that's why there's no incentive for them to actually switch to a dynamic pricing right now. But with the discounts, there is. And for personas, and maybe Roma, you can show the personas right now, who are personas like Sarah, who cares about climate change, but like her primary goal is to save money on the energy bill. So now both interests are combined. Or personas like, and Christopher was the next slide, who is having an electric car, but he wants to charge it with renewable energy. But now he has the control to actually see what's coming out of his socket. Now, did we ask customers and users besides talking to energy retailers? Yes. Maybe Roma, you can show the slide with the link or the questionnaire. So we did a questionnaire, and we asked those questions. How likely is it that you consider to, I can scroll down to the pie charts. How likely is it that you consider actually changing, or do you care about fixed prices? Would you consider to change? What's the most important issue? Like, what electrical devices would you actually switch? And overwhelming majority said, well, in fact, I care about price first, about the climate second, and I would be down to actually switch my consumption, but not for everything, right? I will not stop cooking my meal at 6 p.m., but I would actually try to use my washing machine, my dryer, at a different time if I have the overview of when electricity is green and cheap.
Perfect. That's great that you have all that backup material. Thank you very much.
Thanks.
All right. I guess to stay halfway within the schedule, I would say we have to move on. I think Thomas, Ines, if you can keep your questions and use them in the breakout sessions later, that would be great. And then I would actually jump to our next team, which is QTEX. Guys, if you want to go ahead, take the screen and share your pitch. That'd be great.
Okay, perfect. Thanks a lot. My name is Philip. It's a pleasure to bring to you QTEX today. At QTEX, we are discovering hidden insights within the pharma industry by analyzing phase 4 trial data. For those of you who do not know what a phase 4 trial is, so a phase 4 trial analyzes side effects of drugs that have already been approved and are on the market. Those trials may involve thousands of people, and one major focus is ensuring drug safety. And exactly in the analysis of those trials, we at QTEX see much space for improvement. So one major element of those phase 4 trials is the detection of adverse events. And current methods of adverse events detection are only 95% accurate and mostly done manually. And this inaccuracy leads to pharma companies detecting fatal adverse drug effects way too late, which often results in lawsuits in which they have to pay huge amounts of money for settlements. So one specific example I want to give you here is from Merck & Co., which is, short disclaimer, it's not the real Merck, which is our industry partner, but Merck & Co. And they, for example, had to pay $4.85 billion US for settlements related to their painkiller Vioxx, because Vioxx was causing heavy cardiovascular side effects. And there are many, many more examples just like this. But there's not only a huge potential from a business perspective. So when only looking at the United States, 2.2 million patients are hospitalized annually due to serious adverse drug reactions. And what's even worse is that more than 100,000 preventable deaths related to adverse drug reactions are there annually, and this is only in the United States. So we were thinking, what if there was a method to improve adverse events detection so that many of those unnecessary deaths can be prevented, and pharma companies, on top of that, do not have to pay large sums for settlements anymore? And this is where QTEX comes in. But how do we intend to do exactly that?
We are QTEX. Our goal is focused on using the emergent field of quantum computing to scale and analyze adverse drug safety metrics. For consumers, we hope this means more peace of mind, better patient security, and the ability to use big data to derive hidden cross-influences between different medicines that would be more difficult or time-consuming to detect otherwise. Let's jump into our business model. Our unique selling point is our classification technology using quantum natural language processing. More on this later. Our goal is to help clients improve their healthcare products. We will do this through an initial rollout working with phase 4 clinical trial providers. Typically, when people think of trials, they think of phases 1 through 3. But phase 4, the ongoing market trials, is the largest segment, making up 76% of all trial market share. In this context, we hope to provide better classification for adverse events than conventional methods. In regard to our pricing, we hope to run a tiered pricing subscription model. More on this later as well. We believe our edge in this domain will be low capital intensity, relying only on server-side quantum computing platforms to run our computations through. Additionally, we consider data rights for training and optimization to be the core future of our business, and we'll work to use this to create benefits for consumers. We consider our product to be our classification plus our web analytics platform, and model prices accordingly. We have a 3-month trial, and then we price per trial negotiated with individual firms, depending on factors such as annual revenue, trial size, and trial quantity. while also exploring customer benefit-based pricing when finding statistically significant adverse event reactions. We also work with firms to establish marginal benefits for each trial, leveraging scale for clients. But why do we believe this to be the desired pricing solution for our total serviceable market?
Let's take a closer look at the market. So previous slide, please. So our target customers are mainly large pharmaceutical companies operating in North America. The North America pharmacovigilance market is valued at $1.62 billion in 2020. And specifically, the corresponding software market has a value of $163 million. We expect to capture 5% market share once our company has fostered its position in this market. And this would give an annual revenue stream of more than $8 million. The size of the market is already significant, yet it is expected to expand further at an annual growth rate of between 7 to 8%, and it will reach $220 million in 2025. The main factors driving the market growth include, for example, people's concern with the long-term effects of COVID vaccines, which raises the awareness of drug safety issue in general. And also due to the ever-growing trend of drug consumption, we do see an increase in incidence of adverse drug reactions. And finally, we observed recently that there is a higher demand for electronic reporting in pharmacovigilance from pharmaceutical companies. So the market is really promising, but how are we getting there?
Our goal is to license our technology in long run that scales with the growing healthcare tech industry. The steps would be first to enter the market for phase 4 trials, then continuous testing and improving our model. With our refined data collection, testing, and model training, we will market our classification technology to technology firms interested in expanding into healthcare outcome diagnosis or analytics focused on consumers. Our targets are companies with existing large scalable consumer data sets that are interested in patient health data, for example, Apple, Facebook, as well as any company interested in providing a healthcare analytics platform, for example, IBM, that uses classification as an outcome. We have given an overview. Now let's dive into our demo.
One of the main end users of our product is our patient safety departments. I'm now logged in as John Doe, a patient safety expert in a large pharma company. I sign in into the QTex analytics platform. I see an overview of all the clinical trials my company—
Clarissa, your Figma screen is not visible.
Thank you. Sorry for that. So one step back. So again, one of the main end users of our patient safety department, one of the main end users of our product are patient safety departments. I'm now logged in as John Doe, a patient safety expert in a large pharma company. I sign in into the QTex analytics platform, and I see an overview of all the clinical trials that my company has been monitoring. I care more right now about the one on aspirin because of the recent complaints on severe dizziness. So I click on it, and I see a summary statistics view wherein I can see all the sentences that my company has been logging and how they've been classifying these sentences into either no adverse events found or adverse events found. I see on this scale of adverse events that severe dizziness is ranked highly. I want to know more, so I click on the deep dive tab to find more details. Here again, in our heat map of top adverse events, I see severe dizziness ranked as a large block here. I want to know more, and I wonder if our other clinical trials also have patients complaining of severe dizziness. So I click on the AE tree, and I see here there are various clinical trials that we have. And while aspirin is relieving patients of their moderate pain, severe dizziness is being experienced by some of our patients. If I want to also know how long this has been going on, I go into our time series analysis and see a comparison of the classification of our adverse events on a month-to-month and also year-to-year basis. I see here again that severe dizziness is a point of concern for our company. If I want to know also how our sentences have been classified, I can also go to our Data Explorer, and I see a preview of our data and a classification of our sentences into either zeros or ones. 0 means that our sentence was not classified as an adverse event. A 1 means that our sentence was classified as an adverse event. If, for instance, I want to export this data set, I can simply click on the export button and it will download as a CSV file. But for now, I'm done for the day, so I click on log out. And with the information I've gathered, I can now inform my colleagues and also my company that we need to closely monitor our aspirin clinical trials to prevent any further unwanted patient harm and to also avoid any escalations that could lead to huge lawsuits. I now ask our quantum specialist, how does this all work?
So we want to analyze a text and classify sentences into adverse events and non-adverse events to calculate all the statistics you just saw efficiently and with high accuracy. So how does this work? Clarissa, could you switch the screens again? The main idea is to make use of a representation for sentences that have a natural mapping to quantum circuits. To this end, we use the discogate algorithm that takes the sentences and basically turns it into a string diagram, which you could see on the slide, on the presentation. Clarissa, we don't see a presentation. Could you switch the screens again to the presentation? We still see the Figma.
I'm sorry for that.
But I can already continue. So in our algorithm, we represent words by tensors whose order is determined by the type of word. Interactions are represented by maps, which are contractions that correspond to grammar reductions. So basically here in this example, we have the noun tensor dizziness that interacts with the adjective tensor severe and together with the noun aspirin results in the verb tensor causes. Using then the ZX calculus, we can map the string diagram into circuits and then use variational circuits to optimize the parameters included in our model. Then we can train our model and with the found parameters can classify new sentences. Here on the bottom of the slide, you can see one example of a training graph from just this week, where we trained our model with a mock data set and achieved accuracies of about 97%. However, this is not finalized yet, and we are still working intensely on our model. So why use quantum? What are QNLP specific features?
Firstly, it is grammar independent. By this, what I mean is that QNLP understands the meaning of the words in a sentence and not just search for the word. Secondly, it is NISQ friendly, which means that it is natural and easy to encode language data on NISQ devices in a way that preserves linguistic structure. Experiments involving non-trivial data and complex grammar has already been performed. Next, QNLP has the potential to scale to other domains too, such as automobile, telecommunication, and many more. This is possible because it is quasi-independent of the specific data set. Now, more about our future plan. We are working with very recent research results from just this year by CQC and aim to improve our algorithm along with current research. We plan to have an operational version within a year. We are QTechs, and we would like to thank our industry partner Merck and Bob Koech's team from Cambridge Quantum Computing for their help and support. With this, we thank you for your attention and hope that we could inspire you for our idea. And now we are open to questions, comments, and feedback.
Thank you very much, QTechs, for the great presentation. I think we have the same game as before. If anybody from our jury has a question, just put up your hand. Benjamin, you're first to go.
Yeah, so thank you very much. Well done, team. It was interesting to see that you're progressing well on this QNLP idea. So 2 questions. One is, how many target personas do you expect in the US? So how many patient safety experts actually are available that could use your product? This is question number 1. To nudge you also to maybe a second thought, what do you think would be the broadest possible application for your QNLP concept in other domains?
Excellent questions. So maybe to work on the first one, any patient safety department that is related to phase 4 clinical trials would have perhaps a team of analysts working on drug safety, looking at these metrics, looking at significance, et cetera. So when you incorporate previously sort of analog feedback that a patient would give about, maybe they are sleeping uncomfortably, or maybe they have some sort of headache that is induced from a drug, these things would be now classified and done through our natural language processor in a more automated way. So we would assume that patient safety departments around the country would be very interested in trying this out, especially with our free trial, estimating in the hundreds of firms, as well as the idea of scaling to other domains. One very interesting and keen example we were interested in looking at was the telecommunications department, where we would, for instance, transcribe audio through voicemails or through text messages to parse for certain meanings in sentences. And then depending on if those were spam or advertisements, we could have a smart filter to block out these sorts of messages. So this would be something that we would partner with telecommunications firms in specific.
Great. I guess then, Frank, you would be next.
Yeah, well, thanks for this nice presentation. I didn't quite catch, maybe that was just a bit fast for me. Like, can you just elaborate a bit more on the quantum advantage that you expect? Maybe like compared to the best available classical algorithm, how much faster would your?
I would defer to Federico. Oh, Kevin, yeah.
Yeah, I want to answer that question. So, a quantum advantage. First, I would like to say that speed up is not mainly what we are looking for, although it's proven by theorists that in the longer run, when we have fault tolerance devices, there's at least a quadratic speed up in this QNLP. And also, like, the speed up in NISQ era is not clear, but the advantage we are looking for is mainly about accuracy and sensitivity of the model. And we expect that the QNLP model has like higher expressibility. So with the same number of parameters, it can produce more accurate results. And that's what really the pharma companies mainly care about compared to speed up.
And in terms of your business model, the idea would be to start right away utilizing quantum systems, or would you plan to first have some interim classical solution?
So I can take this question. Yeah, so from the beginning, we intend to offer our quantum service. That's also why we intend to do research and development for long run and seek to enter the market just in 2023 and not too early.
Mm-hmm. Okay, thank you.
Great, then we have Tom next.
Yeah, thanks very much for that presentation. I really enjoyed it. I have a question a bit more pertaining to the field itself of medicine. And what I would like to know, will the solution directly contribute to having checkoffs in the approval process for medicine? Or is this more aimed at improving user inconveniences? And if it's the former, do you need to have any safety checks in place to convince that this particular method of NLP is sufficiently safe to check off the boxes in a medicine trial?
So I would say that like any sort of vetted medical process for drug safety, there should be a component and not an entire aspect of all pharmacovigilance. So since user feedback, like a sentence that somebody describes, is inherently qualitative to their own perspective, if people consistently write that they have dizziness or they have a headache when they take a certain drug, then we can maybe look at that as a point to analyze more concretely and statistically, rather than take it as an objective truth. But these are great ways to sniff and deliver hidden insights in a way that maybe are not as intuitive using currently available analytics methods.
Let me still try to ask that question again, maybe in a slightly different way. Is feedback like this currently taken into consideration? How is it processed? And do you think that this is an acceptable method to entirely replace it? Or will there still be a percentage of humans that needs to check that you also need to factor in for the costs?
Okay, so I can take this question. So right now, the current method to do it is, as I said in the beginning, it's manually, and the accuracy is at around 95%. And what we at QTex hope to do and hope to provide for the pharma companies is to fully automate this process. If there, I guess what you're asking is a bit also about the ethical question. Is it possible to let one algorithm one fully automated process classify those adverse events and then based on this make decisions run? But so this is our intention to fully automate the process. If it's ethically feasible at some point, we will have to check. But for now, it's done manually, and we seek to fully automate the service.
Okay, thank you.
All right, I guess we have time for one or two other questions. Henrik, you would be next.
In the interest of time, I'll just ask one very short and very specific question to Federica, maybe. So first of all, well, great presentation, guys. You really had that together, I think. But so my question is, so there were some proposals for QNLP that were relying on post-selection. Is what you propose now purely variational without any of that, or does it still rely on post-selection?
So at the moment, we are just doing the classification tasks, and at the moment we have not included the post-selection part. Yeah, short answer.
All right, maybe one more, Emily.
Yeah, maybe quickly, could you give us a little bit of insights on how you view competing technologies in the space? Beyond just also NLP, but there are also ways to tackle this with, for example, data sharing and federated machine learning and different approaches that kind of tackle it from a whole other angle. How do you view your position compared to those?
I can take this one. There are more general approaches to kind of data analytics and interpretation of data. And for instance, companies like Cognizant or IBM are providing general solutions for an entire domain space. We have one other specific, we'd say, competitor in the classical realm, and they are Semalytics, and they do more phase 4 related trial data analysis as well. We still think that becoming quantum is the way that we can scale and leverage these insights to a better degree with more inputs for the same amount of processing. So we are closely monitoring the competitor environment, and we want to make sure that we play to our strengths and make sure that we launch one of these products first in the quantum realm.
All right, perfect. With that, third and last team for today, OrganicQ, if you want to take it ahead, please do so.
Thank you, Christopher. I'm going to share my screen now. Okay, hello everyone, and welcome to the presentation of our company, OrganicQ. You might not be aware of this, but we are in the middle of the semiconductor revolution, because more and more often, the material of choice for them becomes organic. And it's not just empty words. 50% of newly produced smartphones already have OLED displays, and this number is expected to grow by 75% in less than 5 years. The organic solar cells follow the same trend. They are not just growing by 34%, they are outgrowing all the other solar cell segments on the market. So of course, the industry is very interested to find new, more efficient materials to capture more value from this growth trend. But the current simulation methods are just not sufficient.
A concrete example of the situation concerns a problem that bothers scientists for many years already, which is the prediction of carrier mobility in devices like OLEDs or organic field effect transistors. So basically, the mobility of a charge-carrying particle is something like the air resistance of your car. So the higher the mobility, the better we can move a particle around in the layer. And of course, then a low mobility means we lose energy to heat, and that is something that we want to avoid. So there have been done many computational studies with common materials, and the general picture is that it is usually possible to predict a right form of temperature dependence for the mobility, but still the actual numbers that you get out of purely simulating results is not something that you can use as a standalone result for your R&D process. So then you have to do experiments, but those are of course expensive, they're time consuming, and thus we want to avoid them if this is somehow possible. Now, the tricky kind of materials that we want to address, they're called single crystal molecular semiconductors. And we want to do this because there is lots of evidence that actually neither of the two most commonly used models that are used in either the organic or the inorganic semiconductor community really describe the physics happening in those materials accurately. So on the one hand, the single crystal molecular semiconductors form big ordered crystals, unlike some of their other organic counterparts where the hopping regime would apply. But on the other hand, the internal vibrations in those materials have a much higher impact than they do in silicon because they are more weakly bonded than silicon. So for realistic materials, in this really very common intermediate regime, we usually need to make very severe approximations in order to handle this problem on a classical computer. For example, totally neglecting the quantum character of the material vibrations. Now, we firmly believe that the key to more accurate results is really considering the full entangling quantum interplay between the vibrations in the material and the carriers in the material. And we want to approach this problem using a very specialized type of quantum architecture that is really built around this physical problem.
This is how we can create new opportunities in the field of material sciences. Our vision is to open a new door in the R&D process of our customers. We offer a high-precision, material-specific quantum simulation framework, which can search large parameter spaces quickly. We want to establish ourselves as experts in the intersection between organic material sciences and quantum computing. We will make use of an analog quantum simulation running on application-specific hardware by our partner, Quantum IQM. In this way, we will translate a material science problem to a quantum device, which uses resonators to imitate lattice vibrations and qubits to imitate electrons. Our quantum solution fits in a multi-stack framework, which as a whole enables explorative scientific freedom. Using density functional theory, we get a parameterized Hamiltonian that we feed into our quantum hardware. Lastly, we can then accurately simulate mobilities in organic semiconductors using kinetic Monte Carlo. In this way, we outsource the part which is classically computationally heavy to our quantum stack.
Okay, so let's see how organic simulations work. Linux is a material science researcher at Aalto University. Linux wants to understand structure property relations in his OLED research. For this, he needs to work to a vast space of compounds and other parameters. However, he is disappointed with existing methods as they are both inaccurate and slow. But he finds organic Q and wants to try it out. After a successful login, he can, for example, run a simulation of fantasy. On the left side, there are files which parameterize the Hamiltonian for the quantum simulation. The files can be recommended from common DFT software. He can then start the simulation. And after the simulation ends, he can also plot the results using the terminal. In this case, the visualized output of the quantum simulation shows transfer integrals that are part of the DFT pre-computed input and the propagation kernel values obtained in the simulation. After that, Linux is also able to run a Monte Carlo simulation on top of the results of the quantum simulation. Linux can then plot the results from the finished simulation, and the output, in this case, is a graph of mobility against temperature.
Perfect. So now that you got a first impression of our solution, let's look at the market potential of what we are offering. So in essence, we are profiting from two major growth drivers in our segment. On the one hand side, we have already seen that there's currently a revolution going on in the space of semiconductors, the organic semiconductor revolution. And that means that the space is actually growing at a very high annual growth rate in the mid 20% range. And at the same time, on the supply side, we also see that quantum computing is gaining more and more traction in the field of material sciences, where the market is actually expected to grow at a 30 to 35% compound annual growth rate. So when we look at the market here and our market size in particular, we expect a moderate market size of 120 million by the year of 2025. But we expect this market to actually explode tenfold to above 1 billion euros in the year of 2030 and above. So we really think, looking at this data, that the time has never been better to actually establish a solid foundation by I'm very sorry, I was just kicked from Zoom, it seems. Yeah, so looking at the data, we think that this is the perfect time to actually get into the market and build a solid foundation for profiting from this tremendous market growth in the future. So by looking at the market here and at the players that are currently operating in the space of material simulations, we deliberately positioned ourselves in a very unique spot here. So what we are doing is we're offering specialized solutions for the niche of organic semiconductors. And this is just a decision that we made deliberately in order to decrease the time to market that we can obtain. So the goal is to develop application-specific circuits, application-specific quantum circuits, instead of general purpose applications, in order to just speed up the development and bring quantum advantage to our customers sooner, following the IQM's co-design approach. And then on the second part of this, or on the second axis you see here, we are also leveraging quantum simulations itself. So we are not trying to simulate quantum effects classically, but we're leveraging quantum circuits in order to achieve much higher accuracy by overcoming the shortcomings of classical solutions, which we presented earlier to you.
Wonderful. So now let's look at our business model. So in the core of our company is, of course, the software development expertise, which we are bringing to our customers, which are both industrial and academic researchers, who are looking to highly accurate simulate the material properties for the organic semiconductors. Regarding the pricing model we chose, we believe that annual feature subscription license is the best choice, because as we will be adding more and more features to our product, our customers will be able to customize what kind of offering they would like to have. So this brings me exactly to our roadmap and what kind of features we would like to have in the future. So we are planning to start with the OLED and open conduction layers, and then we will expand into the two directions. First, we would like to expand our multi-layer stack to move from elementary quantities to the high-level material properties. And second, we would like to add more first-level techniques in order to not simulate just the conduction layers, but also the other layers as well. So in the end, our goal is to become the comprehensive simulation solution for the researchers to explore the complex multi-layered structures. As you can see, we are a team of a very diverse backgrounds, both from business and tech, and we are very excited to tackle the challenge of improving simulation in the organic semiconductor space. Thank you so much for listening, and we're happy to take any of the questions that you might have.
Perfect, thank you, team. Thanks for another great pitch here. I guess, Emily, do you have a question, or is your hand still up? Otherwise, Corey would be first to go.
Yeah, I'll hand over. I think I just don't know how to take my hand down.
Fair enough. Corey.
Okay, yeah, thanks. So first of all, great presentation, super interesting idea. I just had a bit, I was wondering about the technical implementation a bit more, because you had a nice video of the demo. Can you talk a little bit about how you implemented the solution in a small scale way, and what, was it purely classical simulation, or did you use any real quantum computers in this project? Or yeah, can you please talk about that a little bit?
Maybe I can take the last part first, and then Arthur can go into the technical details and how it works. So we are working on a classical prototype. This is of course not a product, but just to show how it scales and how we would use it. And then we plan on working with IQM to implement this on their quantum hardware as it becomes more accessible and useful.
Okay, so regarding the modeling part of your question, basically, we do a two-step approach in order to keep this scalable regarding the qubit and resonator amounts. So first of all, we do a quantum simulation, but we don't really simulate a big chunk of the material using a quantum simulation. But really what we do is we pick out a little cell in the material that is around the size of the mean free path length. And we take this for a time that is around the relaxation time in this material. Because when we do that, if you basically, now this is kind of technical, but if you look at the reduced density matrix of the electrons, then really you should expect that for length scales around the mean free path length and time scales around the relaxation time, this reduced density matrix should have become mostly diagonal and the transport then therefore incoherent. And so basically we do the full propagation of this coupled electron nuclear wave function until this time. Here are also some ways in which we can get those lengths and time scales. So basically the relaxation time can be obtained using just Drude theory in the material, and the mean free path can be estimated from the diffusion constant, which then can again be linked to the mobility using the Einstein-Smoluchowski relation. And so this is how we set the scale for our quantum simulation. And once we finish the quantum simulation, the diagonal elements of our reduced density matrix give us the now classical transition rates we have from the center molecule to some adjacent molecules. And those transition rates we then take into a fully classical kinetic Monte Carlo simulation. So this would be on the next slide. Yeah, so basically now we take a much bigger chunk of the material and we simulate kinetic Monte Carlo trajectories. And basically from the mean squared displacement along the different principal axes in the crystal, we can then get estimates for the mobility along those directions. I hope that made it a little bit clearer why you have the stack of the quantum simulation kinetic Monte Carlo. The gist behind this is really that, of course, we will only have a few qubits and a few resonators at the beginning, so we can't really take many, many molecules and translate them into qubits, but we have to focus on a little chunk, and really we hope that it is enough to just simulate this in a region around the mean free path length.
Yeah, no, thank you, that answers the question. Yeah, great.
Thank you.
Great. Henrik, you would be next.
Yes, thank you for the presentation. So I think it's a great idea, a good presentation. Very nice that you picked something, quantum native. That seems makes a lot of sense. So my question, you touched upon it, but I wasn't very clear. I didn't understand it very well. So you need somebody to supply the testing ground, so to speak, right? Is that completely, are you just offering that software and then Linux from Aalto University just does whatever, or is there some amount of sort of consulting involved where they say they want to have this list of materials, please check for carrier mobility, then you check it, and then you go back and then you iterate back and forth. So is there any of that involved, or is it a pure software and then the customer just does whatever with it?
So I can take this question. I think this is part of our roadmap to start with this very focused quantum solution and then build out this framework so that in the end, the customer can put on some materials and work very freely with the whole 3 stacks. So our plan is to expand this middle stack to all 3 stacks and provide a whole product that provides everything.
Thanks.
I think either Stefan or Benjamin. I'm not sure who's next.
Stefan, go ahead.
I don't mind. So thanks for the nice presentation. I wonder actually how flexible you are in the different choices of materials or problems that you can then solve on this specific hardware, because you said that you have to have this match between your problem and your hardware. So is this then expandable? And can you explain a little bit more about how this would be implemented in hardware?
I think Arthur can maybe explain how we can reduce the problem to a Holstein-Hamiltonian. And we then, when we get this can be implemented directly in an analog way onto a quantum chip. So I think this, from the point on that we have reduced this problem to a Hamiltonian, which is native to a chip with a few resonators or many resonators and many qubits, then it is very freely. Then it's a very free choice in material.
Yeah, so really, once you have a Hamiltonian, you don't have to care about anything that happens before. Still, for those who are interested, so basically, what we do is we have a tight binding model where we compute the transfer integrals between HOMO or LUMO orbitals, depending whether we consider electron or hole transport between adjacent molecular sites. So we do this because we provide like those quantities computed for a unit cell using DFT calculations, which is a very standard step used by many researchers. And so from this Hamiltonian matrix obtained this way, we get the electron part of the tight binding model. And we also then have to do MD simulations of the nuclear movements in order to get, on the one hand, the intramolecular, on the other hand, the intermolecular couplings and phonon frequencies. And that way we get what is called the Holstein-Piers Hamiltonian. So maybe some of you will know more like the Holstein Hamiltonian, because that's the more commonly used model, where we just couple the fermionic occupation operator with a sum of accretion and an annihilation operator of phonons at a specific site. But we also have the intermolecular phonons, which give us so-called piles or non-diagonal coupling. And for this, we basically have almost the same, but we have a hopping of fermions mediated by the coupling to the phonons. And those two parts, as said, we get through classical MD simulations. And this way we get a full parameterization of our Hamiltonian. And these are just numbers that we can then adjust on our hardware in order to get our solution.
Okay, I guess the last question, Benjamin, if you have one.
Yeah, first of all, thank you. I'd like to circle around your strategic approach. So going application specific, I think that's very interesting. And I have one question around the business model. So you mentioned to have a, let's say, standard software business model, license per seat, I feel. But the environment you're in is application specific. So you're targeting very tailored, but potentially very valuable problems. So I used to be a observer in Heliatech, which is an organic PV company. And thus I really know how costly every month can be if you're not able to improve certain durability or performance metrics in your material. The question now is, if you're going for a consequent application-specific strategy, would it make sense as well to tailor pricing application-specific, closely linked to the value your product is delivering?
Benjamin, thank you so much for your question and for the comments. Yes, exactly. We were thinking about this as well. First of all, we chose the feature subscription because, as you could see from the roadmap, we will be improving and adding more and more different simulation. So yes, in the end, the customers will be able to choose, okay, are you only going for OLEDs? Are you going to the OFFETs? Do you need the entire simulation layers? And then based on what value it would create, we will adjust the pricing. So right now we were just looking at the benchmark for similar simulations. But the thing is, as you could see from our positioning, most of our competitors are using the classical methods, which are not really comparable to ours since we use the quantum computing. So when we could sit down with the customers and really figure out how much value we would bring, we would tailor our pricing offering to that.
Okay, Corey, do you still have a question, or is your hand up from before? Okay, perfect. I think we're at time, so it's on me to wrap up. I think quickly want to screen again, but what I want to say is I'm deeply impressed really with what you guys have done over the last weeks and months. It's been really tremendous improvements all over, consistently during the course, I have to say. And especially coming from the midterms now to the final presentation, and also keeping in mind that all of you had to do exams on the side at the moment, right? So there was not a ton of time for all of you. So I think this has been really impressive. I'm super happy with what you've put together. And maybe to wrap it up and to close it down, I want to give the word quickly to your industry counterparts, to your challenge partners. And maybe since Qnamics is first on the slide here, Corey, if you want to say a few words to the team about how the collaboration worked, would be great.
Yeah, thank you. No, I just wanted to say that it was a fantastic last couple months working with the team. As you said, it was not easy due to exams and other ongoing activities, right? But I'm thoroughly impressed with the outcome of the project. And basically, I presented a initial sort of problem formulation, and basically by them kind of digging deep into it and getting down, they sort of massaged it into something much more than the initial kind of nugget of information that we had provided. So I'm really happy with the outcome, and in general it was just a pleasant experience, and I'm so happy and thankful I could participate for a second semester to the course, and I look forward to doing it again in the future.
Thank
Perfect.
you, Corey. Also in the name of the whole Qnamics team, thank you very much for your support, for George's support, Floor's support. It was a pleasure to working with you, and we really want to stay in contact, so let us know.
Amazing, perfect. Thomas, anything from your side?
Yeah, first of all, I love this kind of pitches, and it's really great. And specifically to our team, I mean, we have presented, I think, 200 potential use cases, plus one thing which is a bit of crazy, and of course they went for the crazy stuff. So, and I mean, quantum natural language processing is really not straightforward, and it's a super experiment if it works at all. And since they dared to address this topic, there was really in the background some interesting work upcoming, and we benefit from this. And it's really a promising experiment, and I'm really proud of, to the students to stick with the challenge and not say, okay, we choose something wrong. And also thanks goes to kudos to my colleagues who are really supporting. So we have a quantum, quantum experts in the background, and we have also natural language experts in the background, and we have our drug safety department in the background. So it's not nonsense what we were discussing. And perhaps we find via this channel some investors who help QTex to make it happen in the next 2 years. That would be cool.
Thanks, Thomas. Thanks so much for the nice words. Also from our side, speaking for the entire team, we really enjoyed working with you. Also, Inza and Harsha, I think they should be on the YouTube channel. So also thanks to you for the great insights, feedback, and everything you got. We got from you, and looking forward to the next month that we will work together.
Great. And Ines.
Yeah, thanks a lot. So, well, first of all, I would like to also mention that I completely agree with the fact that the 3 pitches were excellent. So I'm very impressed of the level. It was really amazing. And also I would like to mention that it was such a pleasure to work with the team during these couple of months. I think the workflow was excellent. They were really screening a whole lot of problems in chemistry, the whole landscape, I would say. So the problem that we see today is just one of the many that they were really analyzing very deeply from a technical and business perspective. And it was really amazing, and the pace and the dynamics that they were having. And in that context, I think that the communication with our quantum engineers in IQM, particularly, I would like to acknowledge Vicente, Pina, and Manish Thapa that were supporting them during this process. It was, I think, quite very nice. And yeah, so congratulations to the team, and thanks a lot for this amazing work.
Yes, we also want to thank you, Vicente and Manish, for all the help and support, and we are looking forward to finish up the project strong with you.
We too. Yeah, actually, Jan was mentioning also via chat. Yeah, he's very, very happy of the work and looking forward to keep going, collaborating with you.
Amazing, great to hear all that. And then I think the last thing that I want to mention is we are also very happy if you all stay in touch with us. Of course, there's more to come from this side. So really looking forward to that. I guess at this point, this is where we probably say goodbye to our colleagues on the YouTube stream, and we stop that one. and then we open it up for the breakout session, so you can discuss with the teams directly there if you want to do that.